All right, Math 6610. Switching gears now to second part of inference that we spend a lot of time on in ed research. Is called hypothesis testing. And we're gonna run into this in so many shapes, forms, and sizes throughout the term. Now, what I want to do is I want to start out with just the base example, I guess, is a decent way of putting it, where we have just a claim about a population mean. Now, hypothesis testing, hypothesis is kind of defined as an educated guess. We don't just take a random guess. We have some educated guess about the value of mu. So here's the logic behind it. The central limit theorem tells us that if we took all of the distribution of sample means and create a histogram and smoothed it out, that looks like a ghost. Pretend that's symmetric. It's not, but just pretend it is. Smack dab in the center would be the population mean. And again, if sigma is known, the standard error would be sigma over the square root of n. And we'd model this phenomenon with the z-distribution. If the population's standard deviation is not known, and obviously we cannot use it, then we'd use the next best thing, the standard deviation of the sample, and we would depend on the t-distribution. So since this example here is really unrealistic, we don't run into that much in ed research, we're going to focus on the t-distribution from here on out. So again, these measurements here are all samples. And what we do is we come in and we collect a sample at random. And let's just say it's that one right there. And we compare our sample to the claim. Now, logic would tell you that if our sample mean is close to the claim, it's not justified, if you will, to say this claim is false. But if our if our sample mean is a long way from the claim, it's probably more realistic to think that we're drawing from a distribution with a different mean than it is that our sample came from this distribution. So that's kind of the underlying logic of a test of hypothesis. Now, for the most part, there are 5 steps. The first step is to state your null and alternative hypotheses, what you formally want to test. The next thing we do is we establish our line in the sand. Notice up here I said, well, if this is kind of close or if that's kind of far away, that's pretty vague language, right? We need more structure to our test than just kind of close and kind of far away. So this line in the sand, which is defined by what we call our alpha, it's probability of a type 1 error, serves to be our line in the sand. Again, if we're using a p-value approach. More about that later. All right, the third thing we do is we analyze our sample data. And we, fourth thing we followed up with compare sample data to the claim. And then finally we make a decision. Now it turns out that this 2, 3, and 4 can be done by what's called a p-value approach or a critical value approach. We run into both of these. Primarily in ed research, we use the p-value approach, but I'm going to teach you both of these So you are well equipped. All right. So let's circle back to the GRE. Running out of paper. I believe we'll run out of paper. So let's say that we would like to test that the mean GRE is equal to 600 versus the mean GRE is not equal to 600. Now the structure of the pairs of hypotheses, the null and alternative hypotheses, is here you put a competing inequality. You want to test greater than, less than, or not equal to. Sometimes in ed research there's a justification for greater than or less than. I don't use that. My default is always let's just test not equal to. Because if we want direction, then we can construct a confidence interval later on. For example, in this example, if we got a confidence interval of 610 to 630, it would be reasonable to conclude that the mean GRE is higher than 600 because the entire interval is above. If we got a confidence interval 580 to 595, it would be reasonable to conclude that the mean GRE is below 600 because this interval is completely below 600. All right, more about this stuff later. Next thing we do is we set our line in the sand, and the industry standard for alpha, which we will compare our p-value, more about that later, is 0.05. And I'll go into another video on moving alpha around and what's the advantages and disadvantages of shifting alpha. The third thing is we collect our sample. And what would be interesting to know here is our sample mean, our sample standard deviation, and our sample size. The fourth thing we do is we compare our sample data to the claim, and we'll use what's called a test statistic, and we'll use a p-value. And final thing, decision. If you want to fail 6610, start making goofy remarks down here. The only two things that we can talk about in the decision is we either reject the null or fail to reject the null. None of this, well, the null is true, the null is false. We never know that. We're making a claim about an entire population. We're making a decision based on a single sample. We're just down here doing the best that we can, right? We make errors in hypothesis testing. So we have to lighten the language, if you will. We can't make strong statements. Now, in ed research, if we reject the null, the more appropriate language is to say that we have a statistically significant result. And of course, teaching 6610 reminds me why I'm going into so much detail. I was teaching 6610 a couple years ago and had a student in class, and I don't even want to identify the student, so I'm not going to mention anything about gender, but this particular student was just really struggling, and the person did very well in their other classes. And it dawned on me, unfortunately, too late in the semester, about week 3 or 4, lesson 3 or 4, that this person's base knowledge of statistics was so poor that they were unable to to grasp things when we got into more difficult and challenging aspects of statistics in 6610 and 6620, because we will get into some pretty cool stuff, right? So for this problem, we will set our alpha at 0.05, and we'll officially state what we're testing. So we need to get the mean, the standard deviation, and the sample size. We've already done some of this. So. I'll tell you what, don't we have some other, yeah, we got GPA. Well, I'll tell you what, let's just go ahead and run the, yeah, all right, whatever. So mean GRE is 587.7. Standard deviation we have up there is 115.52. So what we'll do is, again, this is step 3. This would be step 2, just to stick with the method. So we have our data. Now we want to create what's called our test statistic. And this is just really a z-score. But since we're living in, again, the t-distribution, we'll call it a t-score. And what we want is we want to see how far in standard errors our mean is from our claim. Again, the logic is if this mean is relatively close to our claim, we conclude that, well, it's very likely the mean is 600. If this sample mean is a long way, again, quote unquote, from our claim, mu0, which is 600 in this case, then we conclude logically that it's more likely that this sample was drawn from a mean with a different distribution, or drawn from a distribution with a different mean, and this statement is more believable. So we're really deciding which one of these statements is more believable, not necessarily all the true-false stuff that so many people want to conclude. So our 587.70 minus 600, standard deviation 115.52 over the square root of 400. So if we can put that in the calculator without doing something really wacky. And this is what I get, negative 2.13. All right, so this tells me the following. This tells me that our sample mean is 2.13 standard errors below the 600. And again, below because this value is negative. If this value is positive, obviously this number would be bigger, be above the claim. Now the next thing we'll do is we'll calculate the p-value. So again, let me grab another sheet of paper here. The theory behind it is this. We are drawing our sample from a t-distribution, degrees of freedom 399. They've made a claim that the center is 600, which is actually in a standardized distribution, a mean of 0. We have a sample to, what was it, 2.13 or, I've got a calculator. Yeah, 2.13, this is our sample mean, is 2.13 standard errors below this claim. Now the next thing we do is we calculate a p-value. And the p-value is going to be the area under the curve left of 2.13, and because a critical value, or I'm sorry, a test statistic of 2.13, the positive of that, is just equally likely. Again, we get a two-tail test, so we have to account for the options in both tails. We need this area and this area to come together to create our p-value. Well, it turns out this is easy to do. If we do PT minus 2.13, degrees of freedom 399, we will get the area in the left tail. So the area in the left tail is 0.017. Obviously, the area in the right tail is 0.017. If we needed that for some reason, I would have 1 minus PT 2.13, 399, because what the PT function does is it always finds the area below. So if it always gives me the area below and I need the area above, obviously I need to subtract that from 1. And I get the same thing. So I add those two together, so allowing for a little bit of rounding, I get a p-value of 0.034. The next step in the step number 5 is we compare our p-value to our alpha. Well, our alpha is 0.05 and our p-value is less than 0.05, so we reject H sub O. H sub A is more likely. H sub A again is what? That the mean is not equal to 600. Cool, so inquiring minds would probably want to say, well, if it's not 600, what is it? Well, our best guess is, with 0.95 probability, it's somewhere between 576.35 and 599.05. Now, if I'm going to do that on my calculator, I'm going to use t.test. I think I used that somewhere above, right? Or did I ever use a t-test? GRE 600, and I get the values that look very convenient. My test statistic is negative 2.13. My degrees of freedom, the underlying sampling distribution from which we're making these calculations, we're drawing our sample, that's degrees of freedom 399, n minus 1. And our p-value is 0.032, which is very, very, very close to what, I think we got 0.034, my bad. So it's exactly what we had before. I think I'll end there. I really am trying to keep all the videos below 20 minutes. And next thing I want to do is do a prop t-test. And, well, no, I think the next thing I'm going to do is demonstrate this with a critical value. Now, before we depart the video, why does this process work? Because you think if we had 0.025 is our line in the sand, right? 0.05. So we have 0.025 over here and 0.025 over here. If these values are to the left of this line, then this value plus this value has to be less than 0.05. If I get something over here, then obviously the shaded areas there have to be bigger than the 0.025. That's kind of the approach we're going to use for the critical value. But I'll do that in the next video. All right, take care.